Welcome back to our channel. Today we are tackling the derivatives of inverse trigonometric functions. We have already worked with sine x, cos x and tan x, but now we flip things around to their inverses. That is sine inverse of x, cos inverse of x and tan inverse of x. We'll derive the formulas carefully step by step using implicit differentiation. Then we'll solve examples to see how these formulas are applied in general. So let's start with our first function, sine inverse of x. So we'll call this example 1. Example 1. Find, what does the example state? Find the y on the x given y equal to sine inverse of x. So first of all, if we're having an inverse trigonometric function like this, the first step or the first thing we do is apply sine on both sides. That is sine of y equals to the sine of the sine inverse of x, which implies that sine of y equals to x. So after having this, we apply then differentiation. In fact, we differentiate this implicitly. Differentiating this implicitly just as the previous examples. And what was the first step? The first step we had to do was to identify if we already have an equation in terms of y and x, and in this case we have. Our second step was to apply differentiation with respect to x on both sides of the equation. So let's apply that. Applying this, we have derivative with respect to x of sine y equal to derivative with respect to x of x, and deriving this gave us dy on the x times the derivative with respect to sine y on the y equal to the derivative with respect to x of x. This leaves us with derivative of y with respect to x times derivative of sine x with respect to x. Recalling from the derivative of trigonometric functions, this gives us the function cos y equal to derivative of x with respect to x equals 1. This then implies that dy on the x is equal to 1 on cos y. So in this case, we are already having our differentiation, we're already having our dy on the x, but we notice that our dy on the x or our derivative of y is in terms of y, so we need to bring this back to x. So how is this done? So in order to bring this back to x, we are going to use trigonometric identities. So let's recall some trigonometric identities. We all know that sine squared x plus cos squared x gives us 1. This implies that sine squared y plus cos squared y gives us 1. This then implies that cos squared y is same thing as 1 minus sine squared y. This implies that cos y is equal to square root of 1 minus sine squared y. But look at this equation very well. It stated that sine y was equal to x. This then implies that cos y is the same thing as the square root of 1 minus x squared. So substituting this back in this equation, we have dy on the x giving us 1 on square root of 1 minus x squared. So we can then conclude that the derivative with respect to x of the function sine inverse of x gives us 1 on square root of 1 minus x squared. We box or enclose our answers. So let's move on to the second question or the second example on the inverse of the cos function. We'll call this still example 2. Example 2. What does this example state? Find dy on the x given y equal to cos inverse of x. So applying the same steps we used in the previous example, that's in example 1, the first thing to do is send our cos on the other side, or apply cos on both sides, leaving us with cos y equal to cos of cos inverse of x, which gives us x. So we have cos y equal to x. Now the next step is to apply implicit differentiation on this function in order to find our dy on the x. Our first step when we're working on implicit differentiations, our first step was to first of all identify if we have a function in terms of y and x, and in this case we do have such a function. Our next step then was to apply differentiation with respect to x on both sides of the equation. This leaves us with d on the x of cos y equal to d on the x of x, which implies that d on this gives us dy on the x times d of cos y on the x equal to d on the x of x. Recalling the differentiation of trigonometric functions, it was well stated and well proven that the differentiation of cos y gives us negative, the differentiation of cos x with respect to x gives us negative sine x. So in this case, the differentiation of cos y with respect to y gives us negative sine y. So this then implies dy on the x times negative sine y equal to differential with respect to x of x gives us 1. So this then implies that our differential of y with respect to x gives us negative 1 on sine y. So just as the first example, we are still going to use some trigonometric identities in order to express sine x or sine y, in terms of x. So first of all, starting from our first trigonometric identity, which says that the sine squared of y plus the cos squared of y gives us 1. Making sine y the subject of the formula, we have sine squared of y gives us 1 minus cos squared of y, which implies that sine of y gives us the square root of 1 minus cos of y. But we recall that is but cos of y is equal to x, all of this from here. This then implies that sine of y is equal to square root of, here's cos squared, 1 minus x squared. So substituting this back into our equation here, we have implies that dy on the x is equal to negative 1 on sine y, giving us 1 minus x squared. So we can then conclude that therefore d of y on x, which is the derivative with respect to x of the function cos inverse of x, is negative 1 on square root of 1 minus x squared. We box or enclose our answers. So let's move on to the third question, which was on the derivative of the inverse tan function. So we're going to label this example 3. What does this example state? It states find the y on the x given that y is equal to tan x. So for this question, we are going to follow the same steps we used in the previous question. What was our first step? Applying tan on both sides, that is tan y gives us tan inverse of x, giving us with x. This implies that tan y is equal to x. So after this, we move on to our next step, which was to differentiate this implicitly. We apply derivative with respect to x on both sides. D on the x of tan y equal to d on the x of x. This simplifies to dy on the x times d times d of tan y with respect to dy equals to d on the x of x. This implies dy on the x times the differential of tan x with respect to x. Recalling from the video on the derivative of trigonometric functions, it was well stated and well proven that this derivative gives us the function sec squared x. So in this our case, the derivative of tan y with respect to y gives us sec squared y, and the derivative with respect to x of x gives us 1. So just as the previous examples, we are going to use trigonometric identities in order to express sec squared y or sec y in terms of x. So from this, let's first of all make dy on x the subject of the formula. 1 on sec squared y. After making this, we then need to express sec squared y in terms of x. From trigonometric identities, we know that 1 plus tan squared x is equal to sec squared x. But this implies that 1 plus tan squared y equals to sec squared y, but tan y is equal to x. This implies that sec squared y is equal to 1 plus x squared. So substituting this in our equation, we then have implies that z of y with respect to x gives us 1 plus 1 divided by 1 plus x squared. So we can then conclude that is therefore the derivative of y with respect to x, which is same thing as the derivative with respect to x of the inverse trigonometric function tan inverse of x, gives us 1 on 1 plus x squared. We box or encase our answer. So in conclusion, we're able to calculate or able to derive the derivative of the inverse of basic inverse trigonometric functions like sine inverse of x, cos inverse of x, and tan inverse of x using implicit differentiation. And this gave us derivative of sine inverse of x, giving us 1 on the square root of 1 minus x squared, derivative of cos inverse of x, which gave us negative 1 on 1 minus x squared, and derivative of tan inverse of x, which gave us 1 on 1 plus x squared. So we have now derived and practiced the derivative of 3 main inverse trigonometric functions. In the next video, we'll extend this to inverse cot, sec, and cosec, and then we'll tackle challenging application questions. So see you in the next video. Bye.